All right, let's look at inverse trig functions. Not the reciprocals of sine, which is cosecant. Those we have already done that. Inverse trig functions. Let's think about this function. Y is equal to the inverse sine of x. All right, now remember, this means sine of y is equal to x, that for one thing. So x has to be between -1 and +1 because sine of anything is, between these two values. Also, y has to be restricted. Remember, because in trying to define the inverse function, we have to make sure that the original function, the sine function, has to be 1-to-1, which it isn't. So we have to restrict the domain of the original sine function, which is now called y. So y has to be, by convention, by whoever decided to restrict it, so that the sine function becomes 1-to-1, y has to be between -π/2 and π/2. Think of this or this as in this way. Y is the angle for which the sine is x. Okay? Y is the angle for which the sine of the angle is x, and that angle has to be between -π/2 and +π/2. By the way, one more thing we should think about here, and you have to have this picture, okay? And this is something that we do often in mathematics: try to draw a picture and try to figure out what some of these values are. All right, what this says is sine of y is x, right? So y is the angle, and x is the sine of this. That's the opposite if the hypotenuse is 1. All right, so that's given. This picture is given by this equation, which is based on what's given. Y is the inverse sine of x. All right. So now we should be able to figure out this thing. This side is what? According to the Pythagorean theorem, this is 1 minus, or the square root of 1 minus x squared, right? That information is not given to us. Was not, but now we know, right? All right. So with that, we can, we can do this. Let's implicitly differentiate this. What you get is cosine of y. Is that it? No, remember, y is like a function itself. It is. So the cosine of y times the derivative of y. This is something that is unique to implicit differentiation. Now, x simply just becomes 1. And then you can solve this for y prime. You think you can do that? Of course you can do that. It's going to be 1 over cosine of y. That looks simple, but again, remember, y is included in there, and I really don't want to have y as a part of my derivative y prime, because y is equal to sine of x. It would be really nice if I could write y prime in terms of x only and not involving y. So what, you may ask, is cosine of x? Cosine of y. And this picture gives us a wonderful answer to that. Cosine of y is what? Adjacent over the hypotenuse. Right. Adjacent over the hypotenuse. So it's going to be 1. No. What did I say? I said it's adjacent over the hypotenuse. This over 1. Okay, so that's it. So then this becomes 1 over the square root of 1 minus x squared. And that's it. All right. X is going to be. Oh yeah, I said x is between -1 and +1. But here, x can't be 0, right? Well, no, x can be 0. In fact, x can be between -1 and +1. And you notice here, I didn't write the equal sign like this, right? In fact, I'm just going to remove that. Okay, why not? Why do we not want x to be exactly -1 or +1? Well, then the derivative will become 1 over 0, which is undefined. Okay, and actually that makes sense, because if you remember this, the inverse sine function, it looks like this. This is negative. This is +1. This is -1. And as x approaches 1, then the slope becomes positive infinity, right? And that's exactly what you see here. As x approaches 1 or -1, this expression, the slope of the tangent line becomes negative infinite. You have a vertical tangent at these two endpoints. Okay, so that's why you can't allow x to be exactly 1 or negative 1. But this is the explicit formula for the derivative of the inverse sine function. It is an explicit formula in not involving y, but we got this explicit formula for the derivative of the sine function, inverse sine function, using our method of implicit differentiation. All right, once you do this, the other ones are going to be pretty simple too. Next one, let's do the inverse cosine function. Remember again, x has to be between -1 and +1, because this says cosine of y is x, and x is all the value of any cosine function is going to be the value of the cosine function for any input is going to be between -1 and +1. But y is an angle, and for cosine or the inverse cosine, the restriction is from 0 to pi, right? Okay, and also we're going to draw a picture again. This time, y is still in the angle, but cosine of y is x. That means the adjacent side is x, where the hypotenuse is 1, right? Now that gives us the opposite side, which is square root of 1 minus x squared. Does it look okay? Yeah. All right, and now you do the implicit differentiation. This becomes negative sine of y times what? Yes, of course, y prime. I'm glad you said that. I heard you. And then one side is the other side is 1. Y prime is 1 over negative sine of, I guess I can put negative on the top. Sine of y. What's the sine of y here? It's the opposite over 1, right? So this looks very much like this. In fact, it's just a negation or negative of the derivative of the inverse sine function. And again, it may make sense, because if you remember, the inverse cosine function looks like this. Remember, y is between 0 and pi. And so, you know, if you're talking about this and this, the slope is exactly negative. And so that makes sense. Okay, and again, x cannot be -1 or +1, because that leads to 0 denominator, the slope becoming infinite. All right, you can actually do this for all 6, of the inverse functions, but for the inverse cosecant and inverse cotangent and the inverse secant, the restriction gets a little complicated. It's possible for you to do it, but here it's basically enough to do the first 3, sine, cosine, and the tangent. So we have seen the inverse sine, the inverse cosine. Let's finally do the inverse tangent function. This turns out to be quite important. And the fact that I love the inverse tangent function. Historically, this function was used to prove something tremendous about infinite sets. George Cantor proved that the real line has just as many elements as any small interval for which it is only the part. And so that's an incredible statement using the inverse tangent function. All right, that's a historical footnote. All right, so what does this mean? This means the tangent of y is equal to x. This time x can be anything. Did you know that? Because see, the tangent function goes like this, right? From -π/2 to +π/2, and it is 1 to 1 in this interval, in this open interval. So this is the tangent of x. The inverse tangent of x will look like this: π/2, -π/2, and it's this beautifully elegant curve that looks like this. And like I said, it goes from -infinity to +infinity, and it turns out to be 1 to 1 and on to from the real line to this open interval from -π/2 to +π/2, which is what I was talking about in that historical footnote. Okay, all right, so now tangent of y is equal to x. Let's draw a picture of this. This is y, the angle, and the tangent of y is equal to x means this is x if the adjacent is 1, right? Now, we still have the missing, one missing side, which is the hypotenuse. And that hypotenuse now is what? This would be 1, well, square root of 1 plus x squared. For the first time, we see plus because it's the hypotenuse that's missing. All right, let's take the derivative of each part using implicit differentiation. Tangent becomes secant square. And is that it? No, coach, you're screaming, yeah, there should be y prime. Yes, you're right. There should be a y prime, and there it is. If you differentiate x, you get, no, you don't get x, you just get 1, all right? And so y prime is 1 over secant square of y. What is the secant square of y? By the way, you can also write this as cosine square of y, right? Because, I mean, 1 over secant is the same as cosine. What is a cosine of y for this? Cosine of y, according to this picture, is 1 over that, right? 1 over the hypotenuse. So the cosine square turns out to be 1 over 1 plus x squared. Now, this is sort of tremendous, okay? Because for this, unlike the first one, the inverse sine and the inverse cosine, the inverse tangent does not involve the square root, which is much, much nicer. Okay? And if you're looking for a function, if you have this function in particular, and by the way, this function turns out to be pretty important. If you have this function, and if you want to find the function whose derivative is this, then you can say, oh yeah, that's the inverse tangent, okay? So, and that's the second part of Calculus 1 class. Anyway, this is the derivative of the tangent function. X, as I said, can be anywhere, is any real number. There is no restriction on the inverse tangent function because the inverse tangent is defined, like I said here, on the entire real line. And so the derivative of the inverse tangent happens to be 1 over 1 plus x squared, where x could be any real number. All right, maybe we can do a couple of exercise problems before we finish this. Oh, one more thing. As x approaches positive or negative infinity, can you see what happens here? This denominator becomes bigger and bigger, so the y prime goes to 0. And that fact is illustrated by this. Do you see this? Because you have these horizontal asymptotes, the slope of the tangent line or the rate of change becomes closer and closer to 0 over here, and as you go to negative infinity. At x is equal to 0, what's y prime? I'm talking about this point here, okay? This tangent line is like that, and when x is equal to 0, the derivative is 1. So the tangent line here is actually y is equal to x, right, for the inverse tangent graph. Cool. All right, let's do y is equal to the inverse sine of x to the 4th. Can you differentiate this? Of course you can. Can you? All right, so it's going to be 1 over, remember the inverse sine is the outside function. You have to use the chain rule, obviously, right? It's a composition of the 4th power function and the inverse sine function. The inverse sine function has the derivative 1 over the square root of 1 minus x squared. So this is what you have to do, okay? It's you don't write x squared because what you have is y is the inverse sine of the blob. So the derivative is 1 over the square root of 1 minus the blob square, blob being x to the 4th. And then you multiply this by the derivative of the inside function. So the answer is 4x to the 3rd divided by the square root of 1 minus x to the 8th. Okay, and that is the correct answer for that. One last question before we close section 3.8. The derivative of, the derivative of this function, the tangent of x squared minus 2. Let's go ahead and do that. Maybe you can pause this video and come up with your answer, and then you can take a look once you think you have the right answer. All right, so this is a composition of two functions, at least two functions, this being the inside function, but the outside function is the tangent function, tangent of blob. The derivative is secant square of the blob times the derivative of the inside function. Try to write 2x. Oh, I'm sorry. What did I do? Okay, hold on a second. Okay, I didn't do anything wrong except I asked the wrong question for this section. All right, so as I stated, if I ask this question, why is tangent of x squared minus 2? This is the correct answer, secant square of the inside function times the derivative of the inside function. So this is 2x times the secant square of x squared minus 2. Okay, what I was going to ask you, since this is section 3.8, was the inverse tangent of x squared minus 2. If that's the case, what is the derivative of this? Right, the answer, 1 over, now remember, there's no square root for the derivative of the inverse tangent function. So it'll be 1 plus x squared, except it's 1 plus blob square. Okay, and that blob is x squared minus 2. Again, this is according to the chain rule, times the derivative of the inside function. So the entire derivative is going to be 2x over 1 plus quantity x squared minus 2 squared. And that is the answer to that question. All right, I know you have assigned questions, and you should do all of those so that you can master this great skill of implicit differentiation. All right, so next time we'll go to the last section of chapter 3 and learn to differentiate exponential and log functions. That's going to be even better than finding the derivatives of inverse trig functions. All right, I will see you later.